problem. Let linear programming problem. Linear programming problem consists of a large number of variables and constraints. Constraints. It is required to solve solve the LPP by simplex method. It takes a large uh, large storage space and also time overcome this problem. So one such technique is dual simplex method. Uh, in this unit, we try to relate between primal and dual of a linear programming problem, uh, and learn the step-by-step procedure to write the dual of a primal problem. So first we'll discuss about procedure. What is the procedure? Procedure to convert primal into dual. So step one or point number one, the maximization of objective function in primal becomes the minimization of cost cost function in the dual problem and vice versa. Okay. Next, what is that maximization is there? We have to convert into minimization. Uh, second point, the maximization of LPP has less than or equal to type uh, of constraints, while the minimization problem contains greater than or equal greater than or equal type constraints. Suppose less than or equal to is there, we'll convert into suppose in uh, the maximization is there in primal. Dual will convert into minimization. Suppose less than or equal to is there, we have to convert into the greater than or equal to. Then third point, if the primal consists of m constraints and n variables, then it's dual mm, n constraints and m variables. Suppose m constraints n variables, it will convert into n constraints m variables. um, m variables. That is the transpose of the primal problem in the matrix form gives the matrix form of its dual problem and vice versa. So, fourth one, the constants C1, C2, etc., Cn in the objective function of a primal appear on the RHS of constants of the dual. The constants the constraints constraints b1 comma b2 etc bn mm, of the constraints of the primal appear in the objective function, the dual problem. So 5 points we discussed. Next, so procedure to convert primal into dual. So sixth one, what is the sixth? Both primal and dual problems uh, problems problems consists of decision variables uh, that are non-negative. Non-negative means positive. Uh, so procedure to convert primal into dual. Primal into dual. Uh, the relationship between the primal uh, and the dual problems can be easily understood uh, from the below description. So primal variables. Primal variables what we do x1 comma x2 etc xn. So that is row type. Column type is column is dual variables. These are the primal variables. Left side are dual variables. What are the dual variables here? Y1 comma y2, etc. ym. That is inside a11, a12, etc. a21, a22, etc. a2. So am1, am2, etc. amn, 61. Then so on b1 comma b2, etc. So RHS of the primal constants. RHS of the primal constants. Primal constants. Okay. Next C1, C2, etc. Cn. So dual constants. Now the dual of this primal is given by minimize omega equal to b1 y1 plus b1 y2 plus etc. bm ym, subject to a1 y1 plus a11 y1, a22 y2 plus so on, goes like that, plus am1 ym is greater than or equal to c1. So similarly, a12 y1 plus a22 y2 plus etc. am2 ym greater than or equal to c2, greater than or equal to c2, etc. a1n, a y1 plus a2n y2 plus so on, plus am ym greater than or equal to cn. So let's apply this procedure of converting primal into dual to the diet problems. Diet problems. So describe in unit 7. In the unit 7, we have understood the significance and the meaning of primal and dual linear programming problems. In the illustration of diet problem, let's consider the same problem, and we convert the primal into dual as explained below. So here from the table described in unit 7 under 7.2.1, we have F1, F2 means F means food 1, food 2. So vitamin B, so vitamin A, 3 comma, the vitamin A, vitamin B, cost. So vitamin A is 3, F1 3, vitamin B is 2, and cost is 20 rupees. Next, F2, F2, vitamin B 2, vitamin A 2, wait, a printing mistake is there, vitamin A that is. Vitamin B is 2, total cost is 25. So requirement, vitamin B 30, vitamin B 20, 20. So, and units, requirement means units, 3 units, 2 units, like that. So, and given that the cost, and given that the cost of the 1 unit of F1 is rupees 20, and 1 unit of F2 cost is 25 rupees. Primal minimize Z equal to 20x1 plus 25x2 plus subject to answer 3x1 plus 2x2 greater than or equal to 30, 2x1 plus 2x2 greater than or equal to 20. So where x1 comma x2 greater than or equal to 0, x1 x2 denote the number of units of food 1, food 2 and f1 f2 respectively. So dual, in dual primal is primal what is there? In primal minimize z equal to 20x1 plus 25x2 subject to 3x1. Subject to constraints. Subject to constraints. Okay, we'll continue. Here, what we discussed, primal. Primal equal to minimize z, that equal to 20x1 plus 25x2, subject to constraints. What are the constraints here given? 3x1 plus 2x2 greater than or equal to 30. 2x1 plus 2x2 greater than or equal to 20. Where x1 comma x2 greater than or equal to 0. X1 comma x2 denote the number of units of F1, F2 respectively. Dual maximize W equal to 30 omega 1. So you have to read as omega. W equal to 30 omega 1 plus 20 omega 2 subject to constant 3 omega 1 plus 2 omega 2 less than or equal to 20. So 2 2 omega 1 equal to 2 omega 2 plus 25. 25. Here is that is the printing mistake is there 2 omega plus 1 plus 2 omega 2 is here what is there greater than or equal to 20, here less than or equal to 25, here omega 1 omega 2 be the prices of the foods f1 and f2 respectively. So, so the conversion of primal into dual can be denoted as below. Uh, So, table one, primal, uh, primal. So in primal, what is the minimize? Minimize z equal to c power z, c power y x. Uh, this becomes in dual maximize w equal to b square y. Uh, so second such that ax equal to b comma a capital X greater than or equal to 0 as such that a transpose y less than or equal to c uh, uh, and y greater than or equal to 0. Maximize z equal to c power t x that equal to minimize w equal to b transpose y. So such that a equal to b and x greater than or equal to 0, such that a transpose y less than or equal to c and y greater than or equal to 0. So table 2. Table 2, suppose in primal what is there? Maximization problem. In dual becomes minimization problem. In primal, keep in mind in primal always suppose maximization in primal. In dual minimization. Uh, dual minimization. Suppose in number of constants. So number of constants in primal that becomes a number of variables. Number of variables. So less than or equal to constants. Less than or equal to constants. hmm, that equal to negative variables. Less than or equal to suppose like less than or equal to is that negative variables. Greater than or equal to constants. Um, so non-negative, the non-negative, so non-positive variables, non-positive, greater than or positive. Equal constant is there. Unrestricted, unrestricted variables, unrestricted variables. Next, so number of variables equal to number of constants. Number of constants. Non-negative variables less than or equal to constants. Um, non-positive non-positive variables. Non-positive variables. So uh, non-positive variables is greater than or equal to constants. Unrestricted variables equal to constants. So jth variables of objective function, jth variables of objective function, uh, jth constants of the objective function, jth constants of objective function, uh, function 11. So RHS of constants, RHS constants for uh, ith constants, for ith constants, quotient of the objective function, coefficient of objective function. Next, coefficient in constants I, constants I for variables j, variables j. So coefficient in constants j for variables I, j for variables I. Next, so primal, uh, here primal, dual conversion, tabular form, tabular form examples. Is write the corresponding dual of the primal maximize 5x1 plus 6x2 subject to 3x1 plus 2x2 less than or equal to 120. 4x1 plus 6x2 less than or equal to 260 and x1 comma x2 greater than 0. Uh, so solution primal. Primal means here uh, this is the for 8.4.1 example. Write the corresponding the short answer type 5 marks important. Uh, Short answer type 5 marks important. Wow. So once again, I'm reading question example 8.4.1 example. Write the corresponding dual of the primal maximize 5x1 plus 6x2 subject to 3x1 plus 2x2 less than or equal to 120, less than or equal to 12. So 4x1 plus 6x2 less than or equal to 260 and x1 comma x2 greater than or equal to 0. So primal means maximization problem. Max z equal to 5x1 plus 6x2 uh, 5x1 plus 6x2 uh, such that 3x1 plus 2x2 less than or equal to. In dual, what we will write? Maximization means minimization problem. So min z equal to min z star equal to 120 y1 plus 260 y2 such that 3y1 plus 4y2 greater than or equal to 5, greater than or equal to 5. Then 4x1 4x1 plus 6x2 less than or equal to uh, less than or equal then 2y1 plus 6y2 greater than or equal to 6, greater than or equal to 6 and y1 comma y2 greater than or equal to 0. The above problems are explained uh, in pictorial representation below. So pictorial representation means primal problem. So dual problem. So in primal, 5x1 plus 6x2. Uh, this becomes here min z equal to 120 by 1 plus 260 by 2 uh, such that here 3x1 plus 2x2 less than or equal to 120, 4x1 plus 6x2 less than or equal to 260. This becomes 3y1 plus 4y2 greater than or equal to 5, or 2y1 plus 5 by 2 greater than or equal to 6. So hence dual is minimum min z. Min means minimize minimum z star that equal to 120 by 1 plus 260 by 2 such that 3 by 1 plus 4 by 2 greater than or equal to 5. So 2 by 1 plus 6 by 2 uh, greater than or equal to 6. By 1 comma by 2 greater than or equal to 0. Greater than or equal to 0. Example 2. Write the dual of the primal LPP. Maximize Z and 4x1 plus 2x2 subject to x1 minus 2x2 greater than or equal to 2. X1 plus 2x2 equal to 8. X1 plus 2x2 greater than or equal to 8. X1 minus x2 greater than or equal to 10. Uh, so this we need to convert into uh, dual problem. LPP, how to convert it into primer. Uh, so given LPP means linear programming problem. Linear programming problem, that is the primal is rewritten in the symmetric form as follows. Uh, Maximize z equal to 4x1 plus 2x2 subject to constants minus x1 plus 2x2 less than or equal to minus 2. So x1 plus 2x2 less than or equal to 8. Short answer type of question most important. Hmm? So minus x1 minus 2x2 less than or equal to minus 8. X1 minus x2 less than or equal to 10. And x1 greater than or equal to 0. So since x2 is unrestricted sign. So put x2 equal to x2 dash minus x2 double dash. X2 dash and x2 double dash where x2 dash comma x2 double dash greater than or equal to 0. Thus max z max z equal to here max z equal to here max z equal to 4x1 plus 2x x dash plus minus 2x2 double dash subject to minus x1 plus 2x dash minus 2x2 double dash less than or equal to minus 2. X1 plus 2x 2 dash minus 2x double dash less than or equal to 8 minus x1 minus uh, minus 2x2 dash plus 2x2 double dash less than or equal to minus 8. Minus 8. Here x1 minus x2. May x1 minus x2 dash plus x2 double dash less than or equal to 10. And x1 comma x2 double dash comma x2 double dash greater than or equal to 0. So now the dual of the primal can be written as minimum z star that equal to minus 2y1 uh, plus 8y2 minus 8y2 minus 8y3 plus 10 by 4 or 10 by 4. So subject to constraints minus y1 plus y2 minus y3 plus y4 greater than or equal to 4. So 2y1 plus 2y2 minus 2y3 minus y4 greater than or equal to 0. So minus 2y1 minus 2y2 plus 2y3 plus y4 greater than or equal to minus 2 and y1 comma y2 comma y3 comma y4 greater than or equal to 0. Now put y2 minus y3 equal to y. Then the LPP means linear programming problem becomes linear programming problem becomes minimum z star equal to uh, minimum z star equal to minus 2y1 plus 8y plus 10y4 subject to consider minus y1 plus y plus y2 greater than or equal to 4. So 2y1 plus 2y minus 2y4 equal to 2 and y1 y4 greater than or equal to 0 and y is unrestricted. uh, Unrestricted. So what we discussed today, this is 5 marks, very important problem. Uh, 5 marks, very important. 5 marks is very important. Once again, revision what we did discuss today. What we discussed starting. Relationship, unit 8, relationship between primal and real LTPs. Uh, Primal and real LTPs. Relationship between primal and real LPP. Dual LPPs. So, introduction. What we discuss in the let a linear programming problem consists of large number of variables and constraints. Uh, Constraints. It is required to solve the LPP by simplex method. It takes a large storage space and also time. Uh, and also time uh, on computer to obtain its solutions. A few computational methods have been developed to relate between uh, primal and dual of linear programming problem. So and learn the step-by-step procedure to write the dual of a primal problem. What is the step-by-step procedure? Already we discussed. Once again, procedure to solve convert primal into dual. Primal into dual. So first, what is the maximization? Suppose maximization of objective function in primal becomes the minimization of cost function uh, in the dual problem and vice versa. Uh, the maximization of LPP has less than or equal to type uh, type of constraints, while the minimization problem constraints greater than or equal to type of constraints. So if the primal consists of if the primal consists uh, of constraints and n variables, then its dual contains uh, n constraints and m variables. The transpose of the primal problem uh, in the matrix form uh, gives the matrix form of its dual problem and vice versa. So fourth one, the constants C1, C2, etc. Cn in the objective function of where primal primal for of the RHS of the constants of the dual constants of the dual. The constants B1, comma B2, etc. Bm of the constants of the primal appear in the objective function. Objective of the dual problem. Sixth one, both primal and dual problem consists decision variables that are non-negative. That are non-negative. So next, what we discussed, a procedure to convert primal into dual problem. Next, here table one. Uh, Table one. Here table two. Second table primal. Suppose primal in the dual. Primal, what is that? Primal maximization a problem. So in dual, minimization problem. In primal, number of constants. Number of constants. So number of variables. Number of constants, number of variables. So less than or equal to constants. That is non-negative. Non-negative variables. Non-negative. Greater than or equal to constants. That is non-positive variables. Uh, Equal constants. Equal and unrestricted variables. Unrestricted. Number of variables. Number of variables. Uh, Number of variables less than or equal to constants. So non-negative variables greater than or equal to constants. Uh, Unrestricted variables uh, unrestricted equal constants. Non-negative variables less than or equal to non-positive variables greater than or equal to unrestricted variables equal constants. So here jth variables of objective function, jth variables of objective function, jth constant of the objective function, jth constant of objective function, RHS constant for hmm, ith constant, RHS constant for ith constants. So that is coefficients of the objective function for the ith variable. Next, coefficient in the constant for I for variables that equal to coefficient in constant j for variables I, j for variables I. Okay, so 5 marks important. uh, so one problem, uh, 5 marks important. What is that problem? Example, write the corresponding dual of the problem. uh, Maximize 5x1 plus 6x2 uh, to 5x1 plus 6x2, 5x1 plus 6x2, 5x1 plus 6x2, 3x1 plus 2x2 less than or equal to 120. Uh, so 4x1 plus 6x2 less than or equal to 260. And x1 comma x2 greater than or equal to 0. So solution primal maximization problem. Uh, so max z equal to 5x1 plus 6x2 such that 3x1 plus 2x2 less than or equal to 120. This minimization problem. So dual in dual minimization. Min z star equal to 120 y1, 120 y1 plus 260 y2. It's 260 y2. huh? So 3x1 plus 2x2 less than or equal to 120. 3y1 plus 4y2 greater than or equal to 5. One more. 4, that is 4x1 plus 6x2 less than or equal to 260. 2y1 plus 6y2 greater than or equal to 0. y1 comma y2 greater than or equal to 0. Uh, so example, write the dual of the primary LPP. Uh, so maximize z equal to 4x1 plus 2x2 subject to x1 minus 2x2 greater than or equal to 2. x1 plus 2x2 equal to 8. So x1 plus 2x2 hmm, greater than or equal to 8. x1 minus x2 greater than or equal to 10. 10 its solution. So given LPP, the primal is rewritten in the systematic form of the follows. Uh, maximize z equal to 4x1 plus 2x2 subject to minus x1 plus 2x2 less than or equal to minus 2. x1 plus 2x2 less than or equal to 8. So this is minus x1 here minus x1 minus 2x2 less than or equal to minus 8. So x1 minus x2 less than or equal to 10 and x1 greater than or equal to 0. So since x2 is unrestricted sign, put x2 equal to x2 dash minus x2 double dash, where x2 comma x2 x2 dash comma x2 double dash greater than or equal to 0. Thus, thus max z equal to 4x1 plus 2x2 dash minus 2x2 double dash subject to minus x2 x1 plus 2x2 dash minus 2x2 double dash less than or equal to minus 2. So x1 plus 2x2 dash minus x2 double dash less than or equal to 8. So minus x1 minus 2x2 dash plus 2x2 double dash less than or equal to 8. So x1 dash minus x2 dash plus x2 double dash less than or equal to 10 and uh, x1 comma x2 dash x2 double dash greater than 0. So now the dual of the problem uh, can be written as minimum z star equal to minus 2y1 plus 8y2 minus 8y2 minus 8y3 plus 10 by 4 subject to minus y1 plus y2 minus y4 y3 plus y4 greater than or equal to 0. 2y1 plus 2y2 minus 2y3 minus y4 greater than or equal to 2. Minus 2y1 minus 2y2 plus 2y3 plus y4 greater than or equal to minus 2 and y1 y2 y3 y4 are greater than or equal to 0, greater than or equal to 0. So now put y2 minus y3 minus y3 equal to y. Then the LPP becomes minimum z star that equal to minus 2y1 plus 8y plus 10 by 4 subject to minus y1 plus y plus y2 greater than or equal to 4. So 2y1 plus 2y minus 2y4 minus 2 that equal y1 comma y4 greater than or equal to 0 and y is unrestricted. Okay, today we discussed for theory. This is 8 marks, 5 marks short answer type question. 5 marks compulsory question in theory. Okay, so we completed 8th unit. So tomorrow we'll discuss um, 9th unit at the same time. Okay, any doubts? Please ask me or leave the comment. So I'm leaving. Thank you very much.